Good morning, everyone. Today I am going to talk about overall mass balance and continuity equations. So I am Nathanael Villegas Lopez and hope you will enjoy this presentation. So as introduction to simple mass balance. In all fluid dynamic situations, the fluids are in motion. Generally, they move from another place to place and flow throughout different systems. So, as we know, to develop this balance, we have to take into account the input is equal to the output plus the accumulation. If there is no accumulation, which means that is in steady state the operation, the rate of input becomes equal to the rate of output. So there is a specific case when on a simple flow system the fluid enters with average velocity and density. Knowing these two values and the cross-sectional area, we can convert the mass balance equation on this form. So here is the formula. We have the density per the area per the velocity. So with this we can obtain the max flux. So if we need to control the volume for the balance that we are going to do, in this case for a fluid flowing through a conduct, the control surface indicated by this dashed line is the surface surrounding the control environment. This will help us to more easy individual particle identification. So, talking about the overall mass balance equation, we have to take into account the law of conservation of mass before we start to generate these kind of equations. So, taking this into account, we have to the int minus the out plus the generation minus consumption is equal to accumulation. Remember that accumulation is equal to 0 if we are in a steady state. So if we take also into consideration the vector algebra, we recognize that rho v is a scalar of dot product. So the equation from the net max flux in kilograms per second converts on this form with this double integral. So the rate of accumulation of mass within the control volume UV can be expressed as follows. So here is the second formula, and the third formula is the rate of accumulation of mass within the control volume. So we have again some rearrangements to obtain the same formula that we obtained previously. So on average velocity can be used also in overall mass balance. If we assume a constant velocity at a section 1 and a constant velocity at section 2, if the velocity is not constant but varies across the surface area, we can define a new equation taking account also the area and the density. So it is important to also introduce ourselves into overall energy balances. This is the second property to be considered is the energy. So to follow this, we have to know the energy conservation equations, which is here. E is equal to Q minus W. E is the total energy per unit mass fluid, Q is the heat absorbed per unit mass of fluid, and W is the work of all kind done per unit mass of fluid upon the surroundings. So, on derivation of overall energy balance equations, the overall balance for a conserved quantity such as energy is similar to the mass balance equation, and it follows for a control volume. The energy E represented within a system can be classified in three ways: potential energy, which is a unit of mass fluid, kinetic energy by translational or rotational motion, and internal energy, that is a rotational and vibrational energy in chemical bonds. So we have to take also into consideration that the rate of entity output minus the rate of entity input plus the rate of entity accumulation it's equal to 0. The total energy of the fluid per unit mass is E equal to U plus UV squared divided by 2 plus Cg. So we can convert this into a derived formula to obtain the rate of energy accumulation in control volume. We also have to take in consideration two different values important. The work, which is the energy per time, that is divided into mechanical charge, and pressure volume work. And taking into consideration these things, we can obtain the overall energy balance and integrate it. So we have all these integrands, and we will have finally Q minus WS. So, for overall energy balance in a steady-state flow system, we have to know that this is a special case on the macroscope energy balance. So, it is important to consider these single inlet and negligible variations of height, density, and enthalpy across the entire inlet or outlet area. So, it is necessary to integrate the kinetic energy term to obtain this equation that will represent the Q minus Ws. Overall mechanical energy balances. A more useful type of energy balance for flowing fluids is a modification of the total energy balance to deal with mechanical energy. This mechanical energy can include kinetic energy, potential energy, and the flow work part of the enthalpy term. This mechanical energy can be converted into work. So, knowing this equation will become the equation that we have here. So, in the special case where is no mechanical energy is saved and there is no friction, the equation becomes the Bernoulli equation for mechanical energy balance, if we are talking about the turbulent float, which is of sufficient importance to serve future discussions. There is on the left the develop of the equation, or it can be the basic formula that we also know. And that's all. Thanks for listening.